We're going to go through the mathematics of chemical formulas. The approach, all of this stuff you've seen before, so this should be some review. I'm working problems from the homework sheet called Mathematics of Chemical Formulas Review Problems, and I'll go through several of these for you in this video. So let's go ahead and get started. The first one we're going to look at is question number 1. And the question's written right there, what is the mass of 7.5 moles of sulfur dioxide? Now on the top of this page is some stuff that should be somewhat familiar to you. We know that 1 mole of a substance is always equal to 6.02 times 10 to the 23rd of those items. Those could be atoms, those could be molecules, those could be cucumbers, those could be houses. It's just a particle, a thing. It's also 1 mole equal to the molar mass. We get the molar mass from the periodic table. And in the case, if the substance is a gas at standard temperature and pressure, it would have a volume of 22.4 liters. We're generally not going to deal with the 22.4 liters per mole at this point. We'll use that more in the gas laws section. So in order to do this problem, we need to convert the statement into a mathematical expression. What is the mass? Well, that says X grams. Now, the material we're working with is sulfur dioxide. I'm not going to go through a lot of the nomenclature right now, but sulfur dioxide has the formula of SO2. So we want to know how many grams of SO2 are equal to 7.50 moles of SO2. That is the question. Now, in order to answer this, we probably need to figure out what SO2 by itself weighs. So SO2 contains 1 sulfur. That's not the number 15. That says 1 sulfur. And using a periodic table, sulfur weighs 32 grams per mole. So 1 times 32 is 32 grams. The formula SO2 also indicates there are 2 oxygen. That's not the number 20. That says 2 oxygens. Oxygen's atomic number is 8. It weighs 16 grams per mole. 2 times 16 is 32 grams. So that SO2 has a molar mass of 64 grams. So 1 mole of SO2 weighs 64 grams of SO2. It also has an Avogadro's number of particles in it, but I don't probably need that to answer my question. Now the question is, I'm looking for a conversion that relates between moles and grams of SO2. And I have it right here. 1 mole of SO2 is 64 grams. So I'm going to set that up as a conversion. I want the unit mole to cancel, so that will go in the denominator. 1 mole of sulfur dioxide is equal to 64 grams of sulfur dioxide. Moles of sulfur dioxide cancel just like that. At this point, it's a calculator exercise. Take 7.50 times 64, and you'll get approximately 480 grams of sulfur dioxide. And that's your answer to that first question. Okay, I'm going to go ahead and go through several of these for you. I'll try to do them as efficiently as I can so that I don't waste too much of your time. All right, here's question number 4 from that same worksheet. It says how many moles of potassium sulfate is 993.6 grams of potassium sulfate? Well, the question is, how many moles? Now, potassium sulfate, I need to remember the formula. Potassium, of course, is an ion. It's an alkali metal, K1+. And sulfate is a polyatomic ion. You're supposed to remember SO4 2-. So using this, I can get the 1 to come down here, the 2 to come down here, and I end up getting a formula of K2SO4. That's the formula for potassium sulfate. You can't reduce it. The number 2, 1, and 4 as subscripts does not reduce. So the question is, how many moles of K2SO4 is 993.6 grams of K2SO4? That's the question. Now, on the top of this page, I've written down 1 mole equals the molar mass equals Avogadro's number of particles, and if it's a gas, 22.4 liters. Well, in this question, I need a conversion that relates between moles and grams of K2SO4. So I know that 1 mole of K2SO4 is equal to this number of molecules. So I need to figure out the molar mass. So I have to use the periodic table. In the formula K2SO4, there are 2 potassiums. They each weigh 39 grams per mole. So 2 times 39 is 78 grams. There is 1 sulfur in the formula K2SO4. That weighs 32 grams per mole. 1 times 32 is 32. That's up to now 110. And there are 4 oxygens, each that weigh 16 grams, the molar mass, 64 grams. So if I've done that right, that's 174 grams. That's the molar mass of K2SO4. So every 174 grams of K2SO4 is equal to 1 mole of K2SO4. So I'm going to use that as my conversion factor. 174 grams is 1 mole. And I'm going to put that in and do my conversion. Because I have grams up here, I need it in the denominator. So every 174 grams of K2SO4 is equal to 1 mole of K2SO4. Grams of potassium sulfate cancel, just like that. And then if you type that in your calculator, 993.6 divided by 174, you should get an answer of, let me double check here, how about 5.7 moles of K2SO4. 5.701 moles of K2SO4 if we account for sig figs, because we have 4 sig figs here. I could have carried more sig figs. If you would have written 5.7 moles of K2SO4, I would be perfectly okay accepting that for an answer at this point. This is not really about sig figs. It's about how to set up the problems. All right. The next one I'm going to go to is question number 9. Now this one is a little bit different. It says, how many atoms are there in 0.663 moles of water? Now I know what you're saying. You're saying, oh, this one's pretty easy. What I need to do is say, well, 1 mole of water is equal to 6.022 times 10 to the 23rd. And you're going to just go down there and say 1 mole of water is 6.02 times 10 to the 23rd. Now, the particle that we're talking about here, water, H2O, is a molecule. So the particles here are molecules of water. Now, if you stop and get the moles out of there and type that in your calculator, you will not have the right answer. Why not? Well, because in 1 molecule of water, you have an H, an O, and an H, and there's some lone pair. Well, isn't that equal to 3 atoms? There are 2 hydrogens and 1 oxygen. So we need 1 more conversion. That conversion is going to say for every 1 molecule of water, there are 3 atoms. Now molecules of water cancels, and now we can type that in our calculator. 0.663 times Avogadro's number times 3 and you'll get 1.20 times 10 to the 24th atoms. That is the answer to question number 9. Lots and lots of students would forget about this last little step here, right? When you see atoms, if you're dealing with an atom like argon, then 1 mole of Ar does equal 6.02 times 10 to the 23rd atoms of argon. But if you deal with 1 mole of oxygen, O2, that's equal to 6.02 times 10 to the 23rd molecules of oxygen. And then, of course, we know that in 1 molecule of O2, it contains 2 atoms of O. So 1 mole of oxygen is actually 1.204 times 10 to the 24th atoms of oxygen, right? And that's really the game we're playing here, making sure we understand the definitions, the difference between, say, a molecule and an atom. All right. I'll leave the rest of those on the front page for you to play around with. Some of those do deal with volume and conversions, and hopefully you'll be able to get those done. And now I'm going to flip over to the back side, and we're going to talk a little bit about percent composition. Now, I know you remember that a percent on a test is equal to the part you get right divided by the whole that you could have gotten times 100 and add a percent. So if you get 9 questions right out of 10, you didn't get 0.9%, you got a 90% on the test. So using that, let's try to answer this question. Calculate the percentage composition of lithium oxide. Now, of course, we have to first figure out the formula of lithium oxide. Lithium is in group 1, so it's Li1+. Oxide is element 8, oxygen. It ends in IDE, so it's a binary compound. It'll be the element oxygen by itself, found 2 away from its noble gas, so it must be O with a 2- charge. So when they do the crisscross, when the 1 comes down and the 2 comes down, lithium oxide has the formula Li2O. Now, you might look at this and say, oh, the percent composition is 66.7% lithium because 2 out of 3 atoms. Well, that's incorrect. Percent composition always is by mass, always by mass, not by atoms. So that means we need to figure out the molar mass of lithium oxide. There are, in the formula Li2O, 2 lithium atoms. Each lithium atom weighs approximately 7 grams. So 2 times 7 is 14 grams. Of course, in the formula Li2O, there's 1 oxygen. That doesn't say 10, it says 1 oxygen. And oxygen weighs 16 grams. So the total mass of a molecule of Li2O is 30 atomic mass units. 1 mole of these would weigh 30 grams. So if I'm trying to figure out the percent composition, I'm almost done. The percent that is lithium is the part that's lithium, 14 grams of lithium, divided by the whole, 30 grams. And if you do that math there, if you simply go 14 divided by 30, you get 0.463. You have to remember to go times 100, add a percent, 46.3% lithium. Now, I don't even have to calculate the other one. I know the other one must be 53.7% oxygen because the 2 of these must add up to 100%. If I didn't make that connection, I could have found the percent oxygen by taking the part that's oxygen, 16 grams, divided by the whole, 30 grams, times 100, add a percent, and I would have gotten 53.7% oxygen. Okay? All right. I'm going to keep going. I'm trying to keep it at a pretty rapid clip for you. Pause it, rewind it if I'm going too fast for you. All right. Next, let's look at question 17. What is the percent composition of dinitrogen tetroxide? Now, that formula, that compound, has two nonmetals. So we use the Greek prefixes, and what it says is what we have. We have two nitrogens, N2, and we have 4 oxygen, O4. So the formula of this is N2O4. Now, in the formula N2O4, there are two nitrogens. They each weigh 14 grams per mole. 2 times 14 is 28 grams. In the formula N2O4, there are 4 oxygens, each that weigh 16 grams. That's 64 grams. So this has a molar mass, N2O4, a molar mass of 92 grams. If I want to find the percent that is nitrogen, it's the part that's nitrogen, 28 grams, divided by the whole, 92 grams, and then times 100 and add a percent. Well, that comes out to be 30.4% nitrogen. Now, because there's only 2 elements, the other one must be 69.6% oxygen, so that total adds up to be 100%. All right, I hope that's making sense. We have 2 more problems we're going to look at. We're going to look at an empirical and a molecular formula calculation, and we're almost done. Stay with me a little bit longer. Number 21. All right, so we're looking at an empirical formula. Now, in order to get an empirical formula, let me just remind you of the steps of this. And we did this back in probably December. But an empirical formula is the lowest reduced ratio of the chemicals that are in the compound. And the steps were as follows. Step number 1, convert percent to grams. And you use the same number, and you're allowed to do that because we're assuming a 100-gram sample. Assume a 100-gram sample. And if you do that, well, 13% of 100 grams is 13 grams, and so on. Step 2 of this little game that we played said a formula is not a gram formula, it's a mole formula. So convert grams to moles. Finally, the last step that we must do is we want whole numbers, not decimals. So you divide the number of moles by the smaller number, and that will be your empirical formula. Now, there were a few little exceptions. If it ended in a half, a 0.33 or a 0.67, if it added in a half, you had to double everything. If it was 0.33 or 0.67, you had to triple it, and we can play with that if that comes up in the question. So let's go to our question and see what we can do. So it says here the compound is 47.9% zinc and 52.1% chlorine by mass. Well, that's great. Step 1 says just convert those to grams. So that means I really have 47.9 grams of zinc and 52.1 grams of chlorine. That is step number 1. Step number 2 says go ahead and convert those into moles. So I have to use the periodic table. The molar mass of zinc is about 65.4 grams per 1 mole of zinc. And let me grab my calculator here. So if I were to take 47.9 and divide that by 65.4, I like to keep 3 or 4 decimals here. I would get 0.7324 moles of zinc. Now I'm going to do the same thing for the chlorine. Chlorine is element 17. It weighs 35.5 grams per 1 mole. Playing the same game, 52.1 grams divided by 35.5 grams, keeping this to several decimal places, is 1.4676 moles of chlorine. Now, I can't leave it as a formula with decimals, so my last step says divide by the smaller number of moles. In this case, divide both by 0.7324 moles. Divide by 0.7324 moles. This first one comes out 1 zinc. The second one comes out 2 Cls. Putting this together, I get ZnCl2. That is the empirical formula. It cannot be reduced. Okay? Hey, we're doing good. We're 21 minutes into this, and we're almost done. We're going to do one more. We're going to look at 23, question number 23. So it says, what is the molecular formula? Now, the molecular formula is the way it's found in nature. Given that, and we're given some information here, a 212.1 gram sample contains 42.4 grams of hydrogen and 169.7 grams of carbon. And then we're given this other bit of information. The molar mass of our compound is 30 grams. We'll have to add that into our thought process here in just a moment. Now, remember the steps of this. For an empirical formula, said to go first, convert percent to grams. Well, we already have grams. I don't need it. Now, this first bit of information here, this is irrelevant information. The amount of the elements are what I'm interested in, not the sample size. Step 2 on our little journey, step 2, remember, said convert grams to moles. So we need to do that. Well, 1 gram of hydrogen is 1 mole of hydrogen. That's its molar mass. I can do that in my head. That's 42.4 moles of hydrogen. Now the carbon below, carbon weighs 12 grams per 1 mole. So grams of carbon cancel. Better use my calculator. I can't do that one in my head. 169.7 divided by 12 comes out to be 14.14 moles of carbon. Now, I'm close, but remember, in an empirical formula, the third step said divide by the smaller number of moles. So in this case, I'm going to divide both of these by 14.14 moles. 14.14 moles. Now, this top one comes out to be 3.007. I'm calling that 3 hydrogens. And the bottom one, 1 carbon. All right, so I can put that together and I get my empirical formula to be CH3. Now, the empirical formula is not what we are asked about. We're asked, what is the formula of the actual molecule? Now, it's related to the molar mass of the compound of 30 grams. How? Well, let's see. CH3 has 1 carbon, and that weighs 12 grams. And it has 3 hydrogens. They each weigh 1 gram. 3 times 1 is 3 grams. So CH3 weighs 15 grams. But we're told in the problem that this stuff needs to weigh 30 grams. So if we take 15 grams, the mass of the empirical formula, divide that by 30, the molar mass of the actual compound, it goes in 2 times. So we need something that is 2 times CH3. And the way we write that is C2H6. The answer to question number 23 is C2H6 is the molecular formula. And it would reduce to an empirical formula of CH3. All right, lots going on there. I did several of those problems for you. I would ask that you work on the rest of those. Tuesday in class, if you have any questions, I'll be happy to take those from you. And then Wednesday on our short day, we'll have a little quiz over any of this stuff. So as long as you can do these review type problems, you'll be in good shape. All right. Thanks for listening. Have a great day. Bye-bye.